Angular momentum defies gravity and makes tops stable. By Paul Timm and supervised by Dr. Amy Colin. Spinning tops have in the past been mistaken as anti-gravity machines. Rightly so, because they do exhibit counterintuitive behavior. However, their behavior can be understood as an outcome of conserved quantities. As in all closed systems, energy is conserved. It is convenient to break the total energy up into kinetic energy and effective potential. The kinetic energy is dependent on theta, the change in angle between the spin axis and the z-axis. The effective potential has three parts, one of which is the potential due to gravitational force, and the other two can be thought of as potentials due to angular momentum. Essentially, theta is the tilt of the top. Angular momentum is of course also conserved, and as a consequence of rotational invariance, it is constant. If an object's potential energy does not change when the object is rotated about some axis, then the component of the angular momentum along that axis is conserved in time. From Barland 266. Now, an analysis of a conventional top, which turns out to be stable. This is also known as the sleeping top, because it does not precess. A bicycle wheel with an axle makes a very good top. Its spin axis is equal to the z-axis. We will examine the behavior from an energy perspective. Initially, the kinetic energy is zero because the change in theta is zero. The effective potential has three parts, where the angular momentum about the z-axis is equal to the angular momentum about the spin axis because these axes are parallel. The total energy has two terms for the condition that theta equals zero, and because energy is conserved over all times, it will always be constant. It does not change with theta. So it will be graphed as a flat line. However, the energy does decrease as angular momentum decreases. This signifies a loss of energy of the system due to friction at the contact point with the ground. It is hard to see, but there is a vertical asymptote at both 0 and pi over 2. The green line is the total energy, and the red line is the effective potential. If undisturbed, the particle is bounded between the green and the red line. Surprisingly, when we look at this graph, we see that the top is stable. By stable, I mean when disturbed by a change in theta, a tilt, the top will return back to theta equals 0. This is because the slope of the effective potential at theta is greater than 0 and points up, meaning that the top will tend to return to theta equals 0 if disturbed. The position of least energy, the bottom of the well. Now, the angular momentum about the spin axis has been reduced. Friction has caused the top to spin slower. The top is still stable in the sense that it is unlikely to fall if undisturbed. However, it has lost the ironclad stability that it had before. The slope near theta equals 0 is essentially flat. Therefore, if disturbed by a small theta, the top will not fall all the way to pi over 2. However, it will not return to theta equals 0 because it would have to climb back up the well. Angular momentum about the spin axis is further reduced. The slope at theta equals 0 is still very flat, but even at a small theta away, it points down toward an angle of large tilt. Here it seems that the top will fall after the slightest disturbance. Take a look at the phenomena in action. The bicycle wheel will act as a top. Here you can see the wheel spinning fast enough as to be stable. Theta returns to 0. Now the wheel has lost enough energy that it will fall. You can see that it does not return to theta equals 0. On the right, you can see the change in U effective and total energy over time. The bottom of the well approaches pi over 2 as theta approaches pi over 2 for the bicycle wheel. The angle at which the top has fallen over. We have seen that the top is stable for large angular momentums. For large angular momentums, the slope of potential at theta equals 0 is positive. The angle of least energy for spin axis to point is 0, no tilt. This is the case for scenario 1. This is the only truly stable scenario. At these high speeds, no matter how large the disturbance, the top will return to theta equals 0 because it is energetically favorable to do so. In scenario 2, the slope at U effective is 0 is very flat, so the top can sustain a small disturbance without falling. However, it will not return to theta equals 0 because it is not energetically favorable to do so. In scenario 3, the slope of U effective just past theta equals 0 is slightly downward, therefore the top will fall after the slightest disturbance. The minimum angular momentum for stability of the top lies between scenario 1 and scenario 2, when the slope of U effective at theta equals 0 goes from being positive to negative. This can be found by taking the second derivative of U effective with respect to theta to find the point of inflection. Solving for the angular momentum about the spin axis L3 is the minimum angular momentum for top stability. It can be thought of as the critical angular momentum. The critical angular momentum can be used to solve for the critical angular velocity. After solving for the critical angular momentum, which will depend a great deal on the dimensions of the top, including the moments of inertia and the mass, and the radius from the center of mass, a bit of algebra yields the critical angular velocity. Angular momentum equals the moment of inertia times angular velocity, and thus angular velocity can be solved for.